All right, I hope everyone's doing well. It is deep into spring quarter here. I am still dying of allergies. I can see pollen blowing across from you as I walk to campus, as I'm sobbing and crying and sneezing all over the place. So once again, if I'm sneezing and sobbing during the lecture, I'm sobbing not only because the material that we're covering is of that nature, but also because I'm just suffering from allergies. Okay, we've done a lot of problems related to 1D heat transfer, 2D heat transfer. In last lecture, we saw that mass transfer and mass diffusion, the governing equation is the same as that of heat transfer. Now, let's start addressing an interesting problem related to mass transfer. And that problem is called diffusion into a semi-infinite media. And the technique we're going to learn today is called the similarity transform approach. All right. To introduce and motivate this approach and this problem, let's consider a problem that we're at this stage probably tired of solving, which is we have some material. Let's suppose it's a 1D material, where the concentration inside this material varies only along 1D from position x going from 0 to the domain size L. And we like to solve for the concentration profile inside this material as a function of position x and time. Let's suppose that we have the following boundary conditions. We have some inlet concentration, Ca0 over at x equal to 0. It might be some reservoir that some salt or drug concentration is fixed at. And on the right-hand side, the concentration is fixed at 0. Let's suppose that initially, there is no solute inside this material. So there's no solute inside this material at 0 time. And at 0 plus time, we have the left boundary subjected to some constant concentration, the right boundary set to 0. Now let's write the governing equation and the boundary conditions for this problem. It will look something like this. So I have the diffusion equation, where I'm trying to solve for the concentration profile in 1D, partial derivative of concentration with respect to time on the left-hand side, and a diffusion coefficient d, which tells you how easy it is for the solute to diffuse across the material, times the second derivative of the concentration with respect to position x. Now we have one initial condition, that initially there's no solute inside the material. Boundary condition on the left that says that on the left it's fixed at some inlet concentration Ca0, and on the right-hand side at x equal to L is equal to 0 concentration. Now, you know how to solve this problem. We've solved it over and over again. You get a summation of a bunch of Fourier sines and cosines with an exponential decay. Now, in many problems that we like to solve as a scientist and engineer, it doesn't happen to be the case that the domain is fixed at some finite dimension L. Sometimes the domain shoots off to infinity, or approximately shoots off to infinity. For example, if we didn't care about this entire domain, and we only cared about this little patch over here at the inlet, and we wanted to get a very accurate solution near the inlet, then it's kind of overkill to solve the problem all the way from 0 to L. We only want an accurate solution very close to the inlet. So in that case, from the perspective of the material and the solute diffusing through the material, the domain ends infinitely far away. So it's as if L shoots out to infinity. In that case, how would we solve the problem? The only boundary condition that would change is the domain at x equal to L would just shoot off to infinity. So we'd say that the solute infinitely far away is still at 0, except it's no longer a finite space. It's not 1 meter long, it's infinite long. So if we just try to brute force use separation of variables in the Fourier series solution, the solution procedure we've been using for the last couple of weeks, you'd get solutions that look kind of like this. You'd get, sure, you get a steady state, all that stuff. Let's not worry about the details. But the basic form of the separation of variables solution, the transient solution at least, would look like this. A bunch of coefficients, an exponential decay, and sines and cosines. But because now our L, domain size, is jetting out to infinity, if you were to just brute force say, OK, I'm just going to use my Fourier series solution, let L jet out to infinity, then we're going to have sine of a denominator setting out to infinity, and therefore sine of 0. So this would imply that the concentration everywhere would just be like 0, which clearly isn't the right answer. So it tells us that the Fourier series solution works for bounded domains from 0 to L or negative L to L. And that makes sense because we're expressing our temperature profile, our concentration profile, as a Fourier series of sines, cosines, Bessel's functions that are periodic from 0 to L or negative L to L. And therefore, because we're looking for a periodic solution, it works for periodic domain sizes. As soon as the domain shoots out to infinity, we can no longer have a periodic solution from 0 to infinity. We can't have that. And therefore, this smallest change of boundary conditions makes separation of variables and Fourier series completely unworkable. It completely fails. And not fails as in the last time we did it, where the boundary condition on the right-hand side changed to a non-homogeneous value, and that required us to separate the steady state solution from the transient solution, and we could still manipulate it in such a way such that separation variable still works. No. In this case, it actually fails. It completely fails. There's nothing you can massage. There's nothing you can do upstream that can rescue separation of variables in the Fourier series solution in this particular case. So once again, we see that boundary conditions are everything in these types of science and engineering problems. In the case I just mentioned, we just changed the right-hand side from 0 to some non-zero value t1, or in this case CA0, and it changed the way you solved it. In this particular case, we're not changing the right-hand side, we're changing the boundary evaluation point from some finite size L to infinity. That's the change we're making. Everything else, no change. Governing equation, no change. The initial condition, the other boundary condition, no change at all. It's just the evaluation point has changed. And all of a sudden, separation of variables, Fourier series, none of that works anymore. Okay. Now, you might be wondering, well, practically, nothing is infinitely long. So as an engineer, I would never need to solve this problem. I could just use a bunch of Fourier series solution and evaluate for small x, where L can just be 100 meters long, and I'll just evaluate a very, very small value of x, and I'll be happy with. Well, as an engineer, that's a very unelegant solution, because as you've seen, when you actually plot this and code up this summation, you know that for early times and very close to the inlet, you get a bunch of wiggles in your solution. And that makes sense because you're getting a bunch of summations of sines and cosines. It's naturally you see a bunch of wiggles. And at early time, that means that this transient term is still very large. And so for very minor differences in how much weights you put in, how much terms you put in the Fourier series, you get a accurate solution only when you put a lot of terms. So you might need hundreds of terms in your summation to have a very reasonable answer very close to the inlet at early times. Now, as an engineer, you wouldn't want that. I'd want a solution where I can just get a very accurate analytical answer very close to the inlet in this section where practically L has jetted out to infinity. Let me give you a more concrete example of how I might want this and a motivation for why we might want to have a better solution. In drug delivery, we often develop patches. So I might have a little drug patch that I want to put on my right arm. And that patch is loaded with a bunch of drugs. And I want to know how that drug penetrates and diffuses into my tissue. So in this particular case, it might be a situation where I have some drug-loaded patch on the left-hand side, which is fixed at some concentration, Ca0. And this material might be my skin and my tissue. And I kind of want to know how much drug is entering my arm as a function of position and time. And from the perspective of a small little drug inside of a patch, I want to know very accurately the first couple of millimeters inside my arm of what my drug concentration looks like. And from that perspective of a small little molecule of a drug, this arm is so thick, centimeters thick, that the details of that small little sliver is all that matters, and I don't need to care about this centimeter thick material. So that is a system where, for all intensive purposes, this material is infinitely long, and I just care about the drug penetration millimeters in from the outside. Another application might just be like enamel and little paste you put on your teeth when you go to the dentist. A lot of times the dentist, they ask you, do you want to get fluoride? And you say yes, and they put that little fluoride thing on your teeth. And they say, oh, you have to wait 30 minutes. You have to wait 30 minutes because the fluoride's diffusing into your teeth. And you want to wait the diffusion time before you start eating or brushing your teeth. Why 30 minutes? It's this problem. So we have fluoride, a drug, a solid, which is your teeth. Drug is penetrating into your teeth, and you kind of want to know how long you have to wait and how far and how high the concentration of drug that's penetrated into the teeth. So if we can somehow solve this problem and have a nice, accurate solution that we can just plug in our answer into, we might get a very good estimate for how much drug we should load into that patch, or how much fluoride we should put down, or how much time we should wait until we can scrub out that fluoride off our teeth. Okay, so that's why this problem is important. It's used all the time in science and engineering, and also has a really cool connection to random walks and diffusion and Brownian motion. So let's get started with solving this problem. So the Fourier series approach that you're now very good at solving ends up not working when the spatial dimension is unbounded. So it only works for bounded spatial problems because you're putting a bounded periodic domain of sines and cosines that repeat for infinitely large amounts of space. So if it's unbounded to begin with, you can't solve it. Therefore, in a problem like this, where we have an unbounded domain, you can't solve it for that case. And interestingly, this was such a difficult mathematical problem to solve that a lot of really smart people also couldn't solve it. Okay, so it turns out that geniuses like Fourier and Fick also couldn't solve this problem. And like I said, it really troubled a lot of physicists and mathematicians at the time who, again, with seemingly minor little change to the boundary condition, all of a sudden the Fourier series separation of variables approach didn't work. And it was a big conundrum. And a different genius came along a little bit later to actually solve this problem. But before going to that solution procedure, let's think physically, once again, like we always do for all of these problems, about what is actually happening by drawing some profiles. So let's draw some profiles of the concentration along the y-axis as a function of the position x along this domain, for the case of x shooting out to infinity. I'm also going to change the boundary to make it wavy to indicate that it jets out to infinity. All right, for small times, what you'd expect is that the boundary condition pins the concentration at CA0, and then it diffuses only a small distance and continues to be at 0. Just like that. But when you wait a little bit more time, more drug diffuses into the tissue, and it keeps going. Just like that. So the progression of time would be something like this. Now, once again, the boundary jets out to infinity. So the temperature or the concentration doesn't end at some finite length. It jets out to infinity. And all we need to make sure is that when you go infinitely far away, the concentration properly decays to 0. Now, the other genius that, in addition to Fourier and Fick, who couldn't solve the problem, the other genius is Boltzmann. As you might have expected from thermo and statistical mechanics, Boltzmann looked at these profiles and said, oh, it somehow seems like space and time are related to each other. They're interconnected to each other. Maybe I can't specify position and time independently, and maybe there's some relationship between space-time. And he made this observation in the year 1894. And it was 1894, which isn't that long ago, 130 years ago, around then. I don't know. I feel like a lot of these problems have been worked out from centuries ago, from Newton's time, from the 1600s, 1700s. No. This is a relatively recent solution. Recent in the grand scheme of mathematical history, where just 130 years ago, people worked out this diffusion into a semi-infinite media problem. So, like I said, Boltzmann, 130 years ago or so, said, oh, space and time are somehow related. Maybe there's a relationship between the two. So he made a guess that the concentration profile, which is in general a function of position and time, can be written like the following. He posed the question, what if the concentration profile can solely be written as some function phi that's solely a function of a new variable eta? And this variable eta is called a hybrid or similarity variable. And it is written as a ratio of the position x, that's where you are along your domain, divided by some function of time, g as a function of time t. Now, the motivation behind this hybrid or similarity variable is that the observation of space and time somehow being interconnected and related to each other motivates the fact that if you take the ratio of those two quantities of space and time in just the right combination, maybe we can make all of these separate curves collapse right on top of each other. And if we can collapse all of these different curves right on top of each other, we have properly rescaled our solution and collapsed them in such a way that space-time are now connected. And that was the motivation. So, like I've been saying, differential equations are solved by guessing. You can always make this kind of guess. And what we do is to plug it into our PDE and see what ends up happening. So, let's plug in this assumed form of the concentration profile back into this diffusion equation. To do that, we need to evaluate the time derivative and the spatial derivative in the new variable eta. So we need to take a couple of derivatives. First, we need to obtain the time derivative of our concentration. Now, converting over to the real new function phi as some function of eta, we can use the chain rule. This is simply the derivative of phi with respect to eta times partial eta partial time, keeping x constant. Just like that. So keeping x constant, because now eta is a multivariable function of position and time. And this is just a statement of the chain rule. Now we can obtain the partial derivative of eta with respect to time simply from this relationship. So x remains constant. We take the time derivative of inverse g, and we get the following. Just like that. But the goal is to remove all of the x's and times. So let's substitute this similarity variable into x to convert x to eta times g. We get this solution. So all I've done here is to take x is equal to eta times g, plugged it into here. One of the g's cancels, so we get 1 over g. But we get an eta to come upstairs, and we just write the negative sign out in front. So this right here is what will get inserted into the left-hand side of this diffusion equation. Now we need to work on the right-hand side. All we need to do is take two derivatives of concentration with respect to position. Once again, using the chain rule, we have the normal derivative of phi with respect to eta times a partial derivative of eta with respect to position x, keeping time t constant. That's very easy because we have this relationship for eta, keeping time constant. This will just give a 1 over g into the term on the right. Just like that. Of course, we want the second derivative because the diffusion has another derivative with respect to position. So let's take another derivative. All right, so now I've taken a second derivative with respect to position x. I have a 1 over g. I've just put down our solution from above down here. Again, g is not a function of time, and therefore it just came out of this partial with respect to x. And all we need to do is repeat what we just did up here once again. So when you take a partial with respect to x of this term, you'll get a second derivative with respect to eta, and yet another chain rule term over here, partial eta, partial x, with respect to time. So you recover basically the exact same thing we just did once again for this next term. So all you get is another factor of 1 over g out in front. So total, it becomes 1 over g squared. And then you have a second derivative of phi with respect to eta. Once again, going from this step to this step right here is just repeating what you just did. If you can't see it, I just recommend doing the chain rule again to make sure that you see this. All right, so now we have the left-hand side and the right-hand side of the diffusion equation written with respect to phi and g. So let's plug this term on the right-hand side and this term onto the left-hand side, clean up this board, and rewrite this diffusion equation with respect to our new variables phi and g. OK, all I've done here is clean up the board, substituted the appropriate parts into the diffusion equation. So what I've done is to take the left-hand side, the time derivative with respect to concentration, replaced it with the expression that was about right here on the board onto the left-hand side. That looked like this. And the right-hand side, which is the diffusion term on the right, the second derivative of the concentration with respect to position x, that was replaced by an equation that was written about right here on the board, over here on the right-hand side. So all we're doing is taking the original guess, taking a couple of partial derivatives so that we can replace our original equation with this new equation based on this solution phi with a similarity variable eta that is equal to x divided by g of t, some function of time. So we get this expression right here. This is the equation that we are now working with. Now let's divide through by some terms and simplify this a little bit. So what I've done here is to multiply through by g squared. So therefore, the 1 over g cancel, you just get a linear g on the left-hand side. I've divided through by d, brought the negative sign, and the d phi d eta over onto the right-hand side. Now, when you look at this equation, on the left-hand side, we have a term that's a function of time t only. And on the right-hand side, we have another term that's a function of eta only, right? Because g is a function of time t only. So this only depends on time. Over here, if you believe in phi as a function of eta, this term only depends on the independent variable eta. Now, some of you might say, but wait a minute, eta is a function of position and time, so this thing, isn't it also a function of position and time, and therefore you haven't really separated the variables? That's true, but if Boltzmann is really correct that you can write this whole concentration profile not as a separate function of position and time, but only as a function of a single independent variable eta, which is a collapsed version of space and time, then from the perspective of phi, which is the function that eventually becomes our solution, it only is a function of eta. It doesn't know that it's a function of space and time separately. All it knows is that it is only a function of eta. So it's basically saying I can't separate space and time. It only comes as a ratio. So from the perspective of phi, all it knows about is eta. And therefore, you do have a separation of some variable time and some variable eta that have separated. And now we've made this argument over and over and over again, but we're going to make it once more. I have some equation, an equality, where some function of time must equal some function of eta for all time t and all eta. The only way this can possibly be true is if they are both equal to a constant, the same constant. So it's going to be equal to some constant lambda, just like that. And in fact, we're going to go a step further and say that this constant is going to be equal to the number 2. It might sound kind of random. Why would you just say equal to the number 2? Because previously when we did separation of variables, that lambda ended up becoming our eigenvalues, and you had many, many solutions, and that's where the whole sum came from. Not in this case. You're not going to get an infinite summation. It's going to be equal to some constant lambda, and we're going to call that the value 2. I'm not doing a peace sign here. This is the number 2. Right-hand side, that's it. And you'll see why we picked the number 2. It's a purely convenience. You could have chosen any other value if you want. You could have called this pi, e to the 2, whatever. It's just some number. 2 happens to be a very convenient number, as you will see shortly. But the most important idea at this point is that here, just as usual when we did separation of variables, you have 2 separate ODEs. First, we have an ODE in time, and second, we have an ODE in eta. So let's solve those 2 ODEs. That's the time ODE, and this solution, very easy. Nonlinear, separable, first-order ODE. No big deal. You get that. 1/2 g squared is equal to 2 dt. You multiply across, you get square root of 4 dt on the right-hand side, and g of t on the left-hand side. Just direct integration. Some of you might be wondering, but what about the constant of integration? It turns out that constant of integration ends up needing to be 0 for reasons that we'll explain a little bit later when we start applying the boundary conditions. But for now, just think of it as that constant will just later get absorbed into something else. So we don't need to worry about that so much for now. All right. So if this is true, we now know what the function of time is. So coming back to the hybrid or similarity variable, we now have x divided by g of t, which we now know. So apparently, the collapsed variable is one in which the position x is scaled just perfectly with the square root of 4 times the diffusion coefficient times time. So what this means is kind of interesting. It's saying that if I were to take a step closer to the origin by 2 meters, 1, 2, that's identical to waiting 4 seconds. Because I have 2 on the top and I have square root of 4, which is 2. So I still get 1 back again. Or going 3 steps to the left and waiting a unit of 9 time. You get the point. So the idea is when space takes a step, time has to take a square root of that time, which means you have to wait even longer in time to get the same bang for your buck as you move in space. And they're related by a square root. So 2 steps to the left in x means 4 units of time that you have to wait to achieve the equivalent diffusion strength. Okay, it's very interesting. This is where diffusion and random walks all come into play. So this is a very important result that comes when you make the similarity variable for the diffusion equation. All right, now that we know the hybrid similarity variable, and we'll come back. If none of that made sense, that's okay. We'll come back to that concept of taking steps and waiting in time once again. I just wanted to seed that idea of space-time relationship because we now know what the space-time relation is. Let's move on to the ODE for eta because we have another ODE to solve over here on the right-hand side. Let's see what that looks like. We have to solve this ODE. It's got non-constant coefficients. It's a little bit annoying. I don't want to use the power series. Let's make a clever substitution. So now with this substitution of letting y equal to the first derivative of phi with respect to eta, we get this equation, which is a first order linear ODE. Now we can just use the integration factor, directly solve this problem. It looks like this, right? The integration factor is negative eta squared, and you get a constant outside. So this is your solution. Okay, well, of course, y is simply the first derivative of phi with respect to eta, so we just integrate once more. It looks something like this. I've just taken y, which is equal to d phi d eta. I just integrate it directly with eta. And so you get the same constant of integration a times an integral, lower bound 0, upper bound eta, of e to the negative z squared dz plus another constant of integration b over on the bottom right. Now, if you're wondering what z is, that's just a dummy variable. Remember, the integrand is the variable that will go away. So if we integrate over z, the z will go away, and all that we're left with is the variable eta on the upper bound, which is what we want because we want to have ultimately a function phi that only varies on eta. So now some students ask, well, why not just make this z eta directly? Well, it becomes kind of confusing now because I have the bounds 0 to eta, and I have e to the negative eta squared d eta. So there's etas everywhere, and it's confusing what you're replacing, what you're integrating with respect to, and therefore I've made a dummy index z, and the z variable just goes away. You can use another letter if you want, s, e to the negative s squared ds, that's totally fine. It's just a dummy variable. Okay, so this is our solution so far. Now, this term right here, there is no clean analytical integral of that. And it's a function that is a very special function called the error function. And the error function is defined as ERF of an argument, in this case eta, of 2 over square root of pi of the same integral that we have. And this prefactor 2 over square root of pi is included in the definition. So if you go to Python or MATLAB and you type in ERF of an argument, this 2 over root pi is included. Historically, the reason why this prefactor is included is a normalization factor. So if you were to integrate this equation from 0 to infinity, the 0 to infinity of this integral, e to the negative z squared dz, there's that like calculus trick where you convert it into a double integral, x and y, you convert it into a cylindrical polar coordinates, and this whole thing just becomes pi, but then you're taking half of that, so it's root pi over just along the x direction instead of the y, and you get half of that, which is 2. So it's just a convenience to normalize it in just the right way based upon the integral from 0 to infinity being pi. Right? It's one of those like special integrals that maybe you learned about when you did calculus, but it's a cool trick where you convert from Cartesian over to cylindrical, and you can actually analytically evaluate that integral, et cetera, because you get a Jacobian that goes r dr d theta, and then you make a lot of progress. Amazing. Those little math tricks are cool. But anyway, that's why you have this prefactor. But let's graph what this error function looks like. So the graph of the error function. This function at eta equal to 0, the upper bound also becomes 0. It's 0 to 0, therefore there's no area under the curve, therefore the value is 0. Very, very, very far away, it's bounded between -1 and 1. The curve looks something like this. 0 at 0 converges to +1 as eta goes out to positive infinity, converges to -1 as eta goes out to negative infinity. So just remember the bounds. 1, -1, and 0 at 0. Those are the 3 values you need to remember. Now, with this error function definition, we can rewrite our solution like the following. Okay, so now I've rewritten the solution that we have as some constant c1 times the error function, because all we've done is to multiply 2 over square root of pi here, such that we can rewrite it as the error function. And that's why I'm not calling it the same variable. I call it a to c1 because there's a factor of 2 over root pi hidden in there somewhere, just another constant. So c1 times error function of eta. And then just for kicks, I've also called this next integration constant c2. So the idea is you have some error function, constant c1, constant c2 that we need to determine. Now, this is our solution so far, right? I mean, we did a lot of work, but let's recap. We have this diffusion equation we want to solve. We haven't even applied the boundary conditions yet. Forget about the boundary conditions, initial conditions. We're still working on the diffusion equation only, the governing equation. Boltzmann made this guess. We're going to collapse x and t. Space-time gets collapsed into a single variable eta. We plug that solution into our PDE. We separated them, one as a function of time, one as a function of eta. We called that equal to some constant. Okay. One of them gave us a time ODE, which gave us our solution g of t, which is square root of 4dt. That gave us the similarity variable eta. Now, on the right-hand side here, our eta ODE, we solved it. And earlier I said, well, this constant lambda, we just called it equal to 2, but in general, you can call it whatever you want. This is where it enters. So at this stage, this number 2, that came from the choice of lambda. Now, if you notice here, when you integrate this first order linear ODE, you get a factor of eta squared that comes outside an exponential if you make the choice of lambda equal to 2. If you called it some other constant, like pi, you'd get pi eta y, and you'd get a factor of an annoying pi over 2 to factor out here. So you'd still get an eta squared up on top of your exponential, but you'll have an annoying prefactor sitting outside. And for purely convenience reasons, we're going to choose the number 2 so that they cancel, and we only get a very clean exponential to the negative eta squared. Now, like I said, you can choose whatever constant you want, and everything will work out in just the right way that you'll get the same answer. This is purely convenience. OK, the other thing I talked about earlier related to the constant of integration for the time ODE is going to come next, so I'll explain that in a little bit. But for now, the time ODE gave us g of t. We now know what eta is. The eta ODE is our solution so far. So if everything here is correct, then our concentration profile is this right here, C1 error function of eta plus C2. And all we need to do is start applying initial conditions and boundary conditions. But wait a minute, though. If this really is our solution, we have two unknowns. C1 and C2 are our unknowns. But we have one initial condition and two boundary conditions. So we have 3 constraints total that we need to satisfy. But we only have 2 unknowns. Are we overspecified? Normally, yeah, we would be, because we have 3 constraints that we must satisfy. We only have 2 degrees of freedom. How do you specify 3 constraints with 2 degrees of freedom? It's impossible. You're overspecified. And this issue did not come up with normal separation of variables Fourier series, partly because one of the boundary conditions were used to evaluate the eigenvalues. So this constant lambda wasn't just some exact precise number. There were many possible answers where lambda could be true. And the boundary condition was used to obtain one of that eigenvalue relationship. And the other 2, initial condition and boundary condition, obtained the other 2 constants of integration. So clearly, with Boltzmann's similarity method, we've lost one of the degrees of freedom. So are we in trouble? OK, it seems like we're in a lot of trouble, but let's start applying the initial conditions and boundary conditions from the concentration space to this phi space, and let's just see what happens. So I'm going to clean this up, write down the solution that we have here up here, and let's just start carefully applying the initial condition and boundary conditions. Let's first try figuring out boundary condition number 2, which is at the x equal to 0 boundary. On the left-hand side, there is a constant concentration of a solute, say a drug, at CNA. Let's plug in that boundary condition and see what happens. The goal is to convert this boundary condition in concentration over to phi. We need to figure out how does x then convert over to eta, the similarity variable. You can see that at x equal to 0, the numerator of the similarity variable eta goes to 0. And therefore, x going to 0 for finite time is equivalent to eta going to 0, because the numerator x is going to 0. Therefore, we can convert this boundary condition into phi and eta. just like that. So CA evaluated at x equal to 0 for all time should be equal to phi, our new function with the similarity variable eta, going to 0. And this must be equal to the right-hand side, CA naught. So now we can plug in our solution that we have so far, C1 error function eta plus C2 into phi and evaluate it at eta equal to 0. Just like that. Now the error function at eta equal to 0 goes to 0 at the origin. And therefore, this term right here is going to 0. So apparently, what we find is that one of the constants of integration, C2, is just simply equal to the inlet concentration at x equal to 0, or in this case, eta equal to 0. Okay, so far so good. We obtained one of our unknowns using one of our boundary conditions. But we're still not out of the woods yet, because all we've done is to reduce the problem to 2 constraints with only one unknown, which is going to be C1. So how could 1 degree of freedom, C1, possibly satisfy 2 constraints that we still have left? The initial condition and the under boundary condition as x goes to infinity. Let's try first converting each of these boundary conditions and initial conditions over to the phi and eta space, just like how we did here. Now let's consider the other boundary condition as x goes off to infinity. Now, same thing, as x goes to infinity, when you look at the similarity variable, the numerator is shooting out to infinity for finite time, and therefore eta is shooting out to infinity. And therefore, we can convert the concentration of the solute as x goes to infinity into phi of eta going out to infinity. And that must be equal to 0, because infinitely far away, the solute concentration or drug concentration is going down to 0. I'm going to circle this boundary condition. Before evaluating the constant of integration C1 using this boundary condition, let's address the root problem of how do you get 2 constraints with 1 degree of freedom by considering the initial condition. So this is our initial condition. As time t goes to 0, there's no drug anywhere inside the material. Again, let's convert now, in this case, time into what it means equivalently in the eta space. As time t goes to 0, goes back to time t equals 0, you can see here that for finite position x, the denominator, square root of 4 dt, is going closer and closer to 0, and therefore you get 1 divided by 0, which is jetting out to infinity. Therefore, eta is shooting off to infinity as time goes to 0. And therefore, we can convert it over into the phi eta space, just like that. Now, I'm going to circle this one as well, and we can see what happens. You can now clearly see that those 2 constraints are the same. They're identical to each other. Boundary condition on x going to infinity gave us that is equivalent to phi of eta shooting out to infinity. That must be equal to 0. Down here, the initial condition in time told us that's equivalent to phi of eta also shooting out to infinity, and that must be equal to 0. So it turns out it's a very weird situation where a boundary condition infinitely far away is equivalent to time shrinking closer and closer to 0. This is, again, the space-time relation. It's saying that I can go infinitely far away, or I can go infinitely close to time t equals 0 in time, and those are equivalent statements. So it turns out that we're all okay because 2 constraints ended up becoming the same constraint when we convert it over into the phi and eta space. So we've collapsed an initial condition and the boundary condition infinitely far away. This is what's called a collapse of the initial condition and boundary condition. So the initial condition and the boundary condition at x equal to infinity collapsed into a single condition or constraint. And that is the only reason why this all works out.
If this collapse did not occur, then this approach, this similarity transform approach, does not work, because obviously we're overspecified. You can't satisfy 3 constraints with only 2 degrees of freedom. Therefore, this collapse is absolutely critical for us to be able to solve this problem. Now, we're completely in the clear. We have one unknown, C1, with now one constraint, so we can now uniquely obtain what that C1 constant is. So this is the only constraint that we need to satisfy. Let's plug in our answer, C1 error function eta plus C2, which is now CA0, plug in eta going to infinity. Now, the error function, if you recall, juts out to 1 as eta goes to infinity. So this is just 1. It plateaus to -1 at negative infinity, +1 at positive infinity. That's just equal to 1, and therefore C1 is simply equal to the negative of CA0. Just like that, and we have our final answer. Let's write it down. Finally, we have our answer that looks something like this. Ca, the drug concentration at a particular position x and in time, is equal to the inlet concentration of the drug, Ca0, times this factor inside the bracket, 1 minus the error function of eta, which is nothing more than the position x divided by the square root of 4 dt. Now, sometimes this 1 minus the error function of a quantity is called the complementary error function. In a lot of Python and MATLAB languages, it's denoted as ERF with a C. So complementary error function. Now, this overall approach that we took is called the similarity transform, sometimes called the method of characteristics. All right, and the idea behind the naming is that these profiles in time and in space look self-similar. So the self-similarity of each of these curves suggests that they might be able to be collapsed using a similarity variable or a hybrid variable that combines space and time together. And so the key feature of this similarity transform approach is the existence of a collapsed variable, x divided by square root of 4 dt. And I subtly mentioned this earlier, but this is the basis behind diffusion and random Brownian motion. It's saying that position grows like the square root of time. I often think of a drunk person walking out of a bar, taking a couple of steps to the left, and then back towards the right, goes forward, goes backwards, collapses. That spread of that trajectory grows like the square root of time. So the longer you wait, the larger the cloud of trajectory that that individual will take, and it's going to grow like the square root of time. So, similarity transform. The key is the existence of a hybrid variable eta. And what this is saying is that we don't need to know space and time independently of each other. All we need to know is eta, a variable that tells you the ratio, the right ratio of space and time. That's all you need to know. You don't need to give me space and time separately. Eta is all you need to know. So to visualize what I'm talking about, and also to visualize the solution, let's go to the MATLAB code that I've coded up for this solution and see what the actual solution looks like. Okay, what I have here is an animation for the similarity problem, diffusion into a semi-infinite media. I've defined a couple of parameters like the diffusion coefficient of the drug inside the tissue or the material. I've defined the inlet concentration at x equal to L. I've defined my domain, the max time, in the interval of the animation. And I've just literally gonna plot the solution that we just obtained using the error function. And it looks something like this. So what I'm plotting here is the normalized concentration along the y-axis and the position along the x. Now, again, this position juts out to infinity. There is no finite domain in this problem. Okay, so let's play that again. So initially you can see that the profile looked just like what we drew on the board, where the concentration jets down to infinity and stays at 0. but when you get longer and longer in time, the profile goes larger and larger and larger. And you can clearly see that the concentration just keeps growing and growing on the right-hand edge. Of course, I'm just cutting off the plotting, but if you were to plot it over a larger x-axis, you would just see that it juts out to infinity. So that's the key differentiation between the Fourier series finite domain problem and this infinite domain problem. Now, let me just play it out one more time. So a lot of you are probably thinking, oh, this is not that impressive. Yeah, that's because you saw the really cool 2D animation of that amazing color-coded bar plot. So it doesn't look as impressive when you see this one-dimensional plot. It seems like we've downgraded it into a more boring animation. But there's a lot of really cool physics and math in this plot right here. So let me go to a different representation of the solution right here. So what I'm plotting here is the same thing of the y-axis of the concentration, x, and time, divided by the inlet concentration as a function of position x. And I'm plotting here at different time points. So at early times, you're going to see the concentration immediately drops from blue to orange to yellow to purple to green. That's increasing time points. That's what we're familiar with plotting, concentration as a function of position at different cross-sections in time. Now, I'm going to keep this plot, move it over to the left-hand side. And I'm going to plot another one where now what I've done is to plot the same solution, same everything, except I've just taken this x-axis of the spatial position x, and now I've collapsed it into a single hybrid variable eta, the same eta we've been talking about over here on the board, right? We're saying, I'm not going to plot x at different cross-sections in time. I'm just going to plot eta only. So there's no notion of position or time anymore. All you have is eta. And what you end up getting is that all of these different curves, the blue, orange, yellow, purple, green, that used to exist when you plotted time and position separately as an independent variable, all collapse to a single universal master curve that you're seeing right here. So like I said, these legends in different time points are kind of meaningless at this point. What you're seeing here is that the green curve is overlapping all the other curves beneath it. So there's actually a blue, orange, yellow, purple, green curve all hidden inside this single universal curve. So there's actually 5 curves all overlapping on top of each other. But like I said, that's kind of meaningless to think about because there's no notion of space and time as separate independent variables anymore. All you need to know is the single variable of eta. Another way to think about it, because a lot of students seem to find this a little bit confusing, is if you were to select a particular position, say I were to select x equal to 10 on the graph on the left. Now, if I vary the time, I'm going to hit the blue, orange, yellow, purple, green. I'm going to hit all of those points as I go up in time. Now, if I take all those points and replot it with eta, so x equal to 10, divided by all the different time points, that's going to populate the different points along this curve. So you'll get 5 points, boom, 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 5 points along this single curve. And the more time points you take, you'll be able to populate this entire curve into a universal master line. Same with a fixed time point. If I have to fix a particular time, say this purple curve of t equal to 30, and now I'm along that iso timeline, and I'm going to pick different x positions as I go along that line. And if I were to replot it as x divided by square root of 4 dt, it would just fall and populate different lines, different points along this single universal line. So that is the concept behind the collapse of space and time into a single universal variable called eta, the hybrid variable. And with that, there's no notion of space and time separately. All you need to know is the collapsed ratio of space and time eta. Okay, that's all I have for today in terms of the similarity transform. It is such a cool, elegant technique that Boltzmann developed about 130 years ago to get over the subtle little difference in boundary condition. Maybe it's not so subtle. You've taken the finite boundary of L, let it go out to infinity. So, you might say it's not such a subtle difference. But either way, the solution procedure completely is different from the Fourier approach that we've been doing so far. All right, that's it. I hope you have a nice rest of the day, and I will see you next time.